I'd like to thank Herman and his co-organisers for inviting me to such a nice place, and Hart for his wonderful introduction to ITC. So I'm going to concentrate on the spin fluctuations, and that itself is a huge field. So I'm going to just really talk about the high energy spin fluctuations. I'm going to give you a little introduction to neutron scattering as my methodological part. So let's have a look at that. So, so as I said, I'd like to talk about the excitations rather than the spin density wave order that occurs in some parts of the phase diagrams, as Bernhard explained. It's not working. Okay. So neutron scattering goes back to just after the Second World War, just for a little bit of history to start with, when people started doing experiments with the early reactors. And one of the pioneers in that period were Brockhaus and Schall. And here you can see one of the early three-axis spectrometers used for measuring excitations, built in the 60s. Actually, this one is in Canada. Okay. So this is the basic idea of doing scattering experiments. Using this three-axis instrument that I just mentioned, what you want to do is to set up an incident neutron or photon on your sample and scatter it. And if you'd like to do inelastic experiments, you'd like some way of monochromating your particle, your photon or your neutron, and then analysing its final energy. So the first experiments were done like this with crystals to analyse the energy of the neutrons through a Bragg reflection and to create monochromise the beam. So the key thing that we should think about in doing scattering experiments is the excitation, and one looks for a probe where you can sort of forget about what the particle is doing and think about your results in terms of the excitation. So the difference in wave vector here and the difference in energy. So we work out our energy and wave vector from these. Okay, so there we go. If we just reduce it now to the particle coming in and going out, we've got our source, and out we go. So. I'll get used to the clicker in a minute. So. And we usually write the cross-section in this way. This is a cross-section that's the number of particles going in a certain direction in a certain range of energy. And in general, one can write cross-sections like this. This is a cross-section. And one can rewrite this in this way. It's a so-called scattering law. And the idea of doing this is to put all the information about your sample into this S. And this is the cross-section here. And one can show for scattering experiments such as neutron scattering and X-ray scattering that one can do this, and this is what we do. So one ends up with a four-dimensional quantity which can tell something about your excitations here in terms of Q and energy, and so one needs to analyse your data in a kind of four-dimensional way. So one can cut through this four-dimensional phase space and look at your excitations in principle if you populate it so you know this quantity all over the space. So that's what you'd like to do with your spectrometer. So a way to do that in modern technology to get a full picture of your excitations is to use time of flight spectrometers. That's and to have lots of detectors. So a lot of the data I'll show you today is taken that way. So here you can see some spectrometers from ISIS, from the neutron, the spallation neutron source in the UK. And here you can see a gentleman, Rob Bruley actually, standing next to these very tall detectors, and we fill a lot of solid angle with these detectors so we can calculate, so we can measure lots of excitations at the same time and get the most information, the most use of our sample, and cut through all this data. So these are some of the spectrometers that are being used, and I'll show data from those. I'd just like to show what you might see from a single detector, a single pixel if you like. So each pixel you would collect a certain angle, and if you had a fixed instant energy, you would actually sample excitations on a curve like this. This is the Q and energy, okay, going into this detector. And then if you tagged the neutrons with their time of arrival, you'd be able to say where it was on this curve. Okay, and then as you can rotate the sample and basically cut through space with these curves to collect data that shows. So here's an example of some data collected on this spin dimer system by Bella Lake's group, just to show what one can do. You can see here cuts in energy and Q, and some extremely complicated structures that she's able to see using this technique of having lots of detectors and moving the sample around to cut through and measure lots of different excitations. Okay, so that's how we do the measurements with the spallation sources. Just a little bit about how we interpret them. So basics of neutron scattering then, magnetic neutron scattering, are here. So fundamentally the interaction of the neutron with electrons in solid state physics is extremely simple. It's this, it's just the moments of the neutron dotted with the local B field. So you don't usually see it written this way because, of course, if you're measuring spin waves in a material, you don't really think in terms of the B field. We think in terms of the moments, the spins that are producing this B. So one has to reformulate things in terms of the fluctuating moments rather than the field, and that was done very elegantly in the 60s by people like Marshall and Lucy. So we have, but this is the fundamental interaction to think about, and this is the fundamental selection rules, if you like, of neutron scattering. The neutron has spin a half, of course, so we can scatter without changing its spin, or with changing its spin. So magnetic scattering, you can get both of these, and we can separate the two types of scattering by using polarization analysis of the neutrons. So, for example, in an antiferromagnet, one would have two types of scattering. The spin waves would be can be arranged to be spin flip, and the two spin wave excitations, the multi-magnet excitations, where it creates two spin waves together, you would see in the non-spin flip channel. So you can separate these two types of excitation with polarized neutrons. And the other important thing in understanding scattering experiments like this is the generalized susceptibility. So this is just a generalization of the normal susceptibility that you use in a magnet, generalized in the sense that we think about the response not to a constant uniform field, but to a time-varying field which varies in space as well. And then we formulate things in terms of that susceptibility. Of course, that's something that's hard to create an arbitrary one in a lab. You can have a photon, which would be a particular type of time-varying field. But the neutron allows you to create anything you want effectively, and look at this. And then we can split this generalized susceptibility into two parts, the real part and the imaginary part. And of course, it's this imaginary part that we primarily see with neutrons. So this is just the definition of that. So that's the way we think about neutron scattering, particularly in metals where you have diffuse scattering. This is an important concept to use. So just a couple of transparencies about what that means physically then. Of course, I think most of what I'm going to say today you can think of in terms of a damped harmonic oscillator, a very useful tool in physics, of course. Here we have the equation for it. And here is response functions. This is the susceptibility for the damped harmonic oscillator, the damping coefficient and the natural frequency here omega naught. So this is the response function then that's appropriate to thinking about an excitation in a solid. One can write it in this compact form here actually. This is now the real part, which is response here. And then we've got the damping and the frequency here. So you see that actually it's very useful. This bit here actually was very useful. Another useful thing in neutron scattering, the Kramers-Kronig relation, which relates what we measure with neutrons, the imaginary part, to the real part, which is often comes in handy. In the limit of 0Q, this would just become the null susceptibility. But if one looks at fluctuations, just thermally induced fluctuations, for example, when you measure a correlation length, it actually is the real part that's relevant. Actually, Cyril made a remark this morning about correlation lengths in observing neutrons, which this is related to. I'll mention a bit more about that in a minute, but he said this was he said quite correctly that this was quite short in CUPRATE superconductors, but actually this other part here can be quite long. You can get very structured excitations, as I'll show later on. So this part allows you to connect those two bits. Okay. And you'll see this is quite a useful way of plotting these functions as a function of damping the response here. So here I've plotted the response of different harmonic oscillators and changed the damping, and you can see you go from obviously a sharp peak to this Lorentzian peak when it's overdamped. So we find that the excitations of CUPRATE superconductors are somewhere on this scale. They're highly damped, but not necessarily overdamped for a given Q. So this is the picture that we have. But finally, just for completeness, another useful tool in scattering experiments is the fluctuation dissipation theorem here, which allows us to relate the susceptibility with a Bose factor to actual fluctuations in moments. So this is like the power spectrum, we call it, of the moment fluctuations in our solid, can be related to this quantity. And this quantity is actually what we measure. Another way of seeing neutron scattering is to say this: we measure this quantity, we can remove this, what we call the Bose factor, the one that's used for neutrons here, and obtain the response susceptibility. Okay, here's just a zoology, as I call it, of what we see when we measure response functions in different types of magnetic material, to show what one might expect if you're looking at some new material like a high temperature superconductor. So if we start with a metal, just to begin with, what you see in a metal is a particle-hole continuum, a broad scattering, say in something like sodium. This would be very broad, going up to electron volts. If you've got correlations in your metal, you're going to lower this down, and you see this. And then if the metal has Fermi surfaces, you might see some structure due to nesting, transitions across different bits of Fermi surface. So in something like chromium, you would see extra peaks due to this. So that's the metal. In some in chains of antiferromagnets, one-dimensional chain, you might see diffuse excitations like this, and Here's some classic things which are relevant. Even in a ferromagnet, of course, you see spin waves going across the Brillouin zone here. One would see a ferromagnetic spin waves like this. On an antiferromagnet, we would go across the Brillouin zone here to this would be the ordering vector, and you would see spin waves that dip down in the middle. So this diagram here is actually something to remember for the cuprates then. If we have a square lattice with antiferromagnetic order along the one direction, then you get antiferromagnetic order here at a pi, and you get spin waves going across this line here, as you see here. The intensity of the spin waves would vary. They'd be strongest in this zone here, near the order, and very weak in this zone over here. Although this is still an excitation away from the order here, you can't excite it with neutrons. It has a low susceptibility. So let's look at how this maps onto cuprates. So this is the phase diagram that Bernhard showed in his last talk, just illustrating the IPCO. So I'll talk a bit about IPCO in a minute. Just to remind you then, if we want to measure the excitations across here, just to try and understand why one might get this high transition temperature and how the excitations might vary as we go across this, that's what we'd like to do. So I'd like to start with the antiferromagnet, and I'll show you different data for the underdoped and optimally doped superconductors to show you how things evolve across here. Of course, one can get, in fact, let me switch to the next one. This is IPCO. For LUSCO, the phase diagrams like this. So again, we've got the antiferromagnetic phase, and we have a region here in the middle where we have this stripe order, or stripe fluctuations of some sort. This is, as Bernhard explained in his talk, this is a unique thing to the lanthanum-based materials because the octahedra can rotate and they favour having a spin order connected to the charge order. But apart from that, we've got this dip in the TC again because of the competition with the charge density wave, and we'll look at the excitations across here. So let's start with the antiferromagnet. So so there's a few materials where we've the excitations throughout the Brillouin zone have been measured for the parent compounds. One of which is LUSCO here. So this is some of our own work where we've measured the excitations throughout the Brillouin zone. This is the structure then. You can see the copper oxide layer here with these spins anti-parallel along this direction, along the bond direction, giving you this bragg peak in the middle. So this is what you'd expect the spin wave excitations to look like, as I showed you before. This is now a two-dimensional diagram, obviously, and they're strong in the middle here. So this is the measured dispersion we have, and you can see the excitations are stronger at the half-zero position than the positions like quarter-quarter or three-quarters quarter. So this difference here indicates that there's some extra exchange. There isn't just a nearest neighbour exchange constant. In fact, you have to take into account next nearest neighbour exchange to account for the dispersion in the parent compound. So that's going to the next copper here, or around 90 degrees, or so-called cyclic exchange all the way around. They all contribute to this dispersion. But the main point I'd like to make here, actually about the parent compound, is that the spin wave excitations are already pretty anomalous in the parent compound. So one would expect for an antiferromagnet just to have spin waves dispersing throughout the Boolean zone and some what we call two magnon scattering above. But what we find in lithium cuprate, and you can see this diagram here, at the half-zero position, is that the excitations are very strongly damped. This lighter blue colour here, compared to, say, here, we see this extra scattering above the spin wave, showing that there's, the spin wave is damped, or it's almost falling apart. If we look at the intensity of the spin wave pole, so we pull out the actual excitation on this dispersion curve and fit it to the to a function with the resolution width, we can see that it drops down to about half of what you'd expect from the spin wave theory. So even in the parent compound, these spin waves are pretty anomalous. Let me show you some more evidence for that. So what I'm going to show you now is, if we, instead of plot it like this, if we choose particular points in space, look at those, or we make a map for particular energies. So the energy where we have this anomalous scattering is at a half-zero. So if we make maps, constant energy maps, what we will see is a little blob that exists at that energy for lots of energies, as if there's a kind of rod of scattering going up in energy from this point. And you can see that here. The highest energies, say 300 millivolts up to maybe 400 millivolts, there's this rod of scattering, and that's the anomalous spin wave. The rest of what you see here is just the normal dispersion of the spin wave as we go up in energy. So these blobs here are another way of seeing that effect.
Is this intensity somewhere observably recovered?
Yes.
You know where?
It basically goes to higher energies.
Even higher energies?
Yes. Yeah. It's difficult to know how much it's spread out around in Q at the same time, but we can see this high energy tail basically goes as high as we can see with neutrons, and more recently people have been doing RIXS experiments, and they see it go to even higher energy. So you can see that to some extent here. Here's our magnon pole. It should be about the same width of this one. This is measured quarter-quarter, and you see this tail here? This carries on. So these are the magnons measured at 2 points in reciprocal space. This one here is the more damped one. Even this one may be a little bit damped. This is probably more like the conventional two magnon scattering. But this is, there we go, this is our anomalous magnon. So what we see here isn't unique to cuprates, though, actually. It's now known, well, in parallel, the work was going on square lattice anti-spin-half antiferromagnets with much smaller exchange constants, such as deuterated copper formate here. I haven't put the reference. This is from various collaboration involving Henrik Bono and Desmond Morrow, various people. They've been working on this compound here, which has got a much smaller J. It's also square lattice with copper spinner halves. So they can see exactly the same effect. So it seems to be a generic effect of the spinner half square lattice. You see the tail here in this, and now this is down at like 15 millivolts instead of 300 millivolts for the cuprates. The advantage of working at the low energies is they're able to separate the excitations into their two constituent parts, the transverse excitations like the spin waves and all the other stuff in the longitudinal fluctuations. The fluctuations parallel to the moment, the order moment is this, and these are perpendicular ones. So that's generic behaviour of the spinor half. That relates to a remark by Seamus this morning. He mentioned Phil Anderson's picture of spin-ons in the resonant valence bond model, what we believe actually now is there are spin-ons in lanthanum cuprate, even in the parent compound, and you can see that spin-ons are much more clearly manifested in one-dimensional spinor half chains, such as this one here. This is potassium copper fluoride and some work from Bella Lake, and she's mapped out the continuum that you get. So this is a much more extreme version of what you see in lanthanum cuprate. So spin-ons are fractionalized excitations, spinor half excitations instead of spin 1 excitations like spin waves. In the simplest picture, the spinor half excitations would bind up to form spin waves. That's what would normally happen, but they don't quite do that in lanthanum cuprate. Obviously, when you dope the compound, now you create potentially even more of these things, and that's the sort of way you're coming from, we believe, for lightly doped cuprates. Okay, so that was all neutron scattering so far. I'd like to just mention some resonant X-ray.
Stephen, one quick question. In the previous example, not the 1D1, the previous one before that, the line shapes are not very, let's say the longitudinal line, they are not very Gaussian.
No.
Is that indicating multivariable scattering?
This is the sort of quotation marks spin-on-like line shape.
Oh, this is still 1D?
No. We believe that it's not 1D, but it's going that way. So the line shape, the actual excitations are not nice Gaussian spinors. They naturally have this tail, and that occurs in both channels actually. If you look at the transverse one and the longitudinal one are not, the line shapes are not normal line shapes. Yeah, so that's the sort of, I think it's just an important message maybe that even in the parent compound, it's anomalous, the excitations. Okay, so Bernhard mentioned the magnetic X-ray technique. So this is a technique that's come along in recent years, primarily because the resolution of the instruments has become very good. So we now have resolutions of about 40 millivolts. In fact, the neutron scattering data I showed you at the highest energies has the same resolution now as the X-rays. Of course, neutron scattering, you can improve the energy vastly by just making the energy of the neutron smaller. But when you go for high energy neutron scattering, you're stuck with very high energy neutrons, and the resolution is similar to what you have with RIXS. So you can go to the L resonance of copper and sensitize yourself to magnetic excitations using various spectrometers. Here's the RIXS spectrometer. This is the ID32 at the ESRF. Basically the same principle as neutrons. We define the Ki and Kf very precisely. So here's some work on lanthanum cuprate now with RIXS. Actually, this is some of our work. It's not the first work. There's early work by Brakovich and collaborators on lanthanum cuprate back in 2010, and since then new instruments have come along, and also from Bernhard's group and collaborators, they did the early work on IRCO material. But here you can see now the spin waves in the parent compound measured with RIXS. You can see the difference in the energies between the 2 points. You can also see the higher energy diffuse scattering with the RIXS. Okay, so I've told you a bit about the parent compound now. I should have had this little pause there, so reset your brains, because now we're going to go on to the superconductors. So this is going back in time to some of the early work from Gen Shirani at Brookhaven. So unlike the CUPRATE, so at low energies, he found that you have these incommensurate peaks. If we scan through near the center of the Brillouin zone, we see two peaks in nearly optimally doped LUSCO, and he found that as you raise the temperature, these get more diffuse, and they exist at different energies here. So so it goes right back to the 80s. The observation of the low energy scattering in the CUPRATE. Here's some more recent data taken with spallation source on a similar composition. So here you can see a map of those four peaks. In this is H and K, and this is the zone center here. So you see at low energies now the peaks have moved away from pi or half and half. And then as you go up in energy, you actually see these incommensurate peaks existing up to about 25 millivolts in this material. And then above that, you see a blob appearing in the middle, and it gets broader and broader. And at the top here, it's like a circle. And here you can see some data. I'll show you some cuts to this in a minute. But I'd just like to mention this point about correlation lengths that Cyril mentioned, which is an important point. So this is, if we add up all this stuff, we're going to get a very long correlation length. But if we're interested in the excitations, if we're interested in the thermodynamic properties at low temperatures, for example, explaining that peak in specific heat we saw, then it's not all this stuff that's important. It's actually the low energy excitations that would be the ones that would determine what's going on. And these are quite sharp, in fact. So this isn't the width of these is not a correlation length, it's the width of the response function at low energies. So that can be many lattice, 10 or more lattice parameters long at low energies. Here's some more, this is basically now the same sort of data plotted across the phase diagram. So what I've done here, this is raw data, and what we've got here is a cut in going through the middle of the Brillouin zone along the bottom, and energy up here. And this is a very sort of sharp thing, splitting a bit at the top there. This is the parent compound, and then we're increasing doping here. You can see this is all on the same scale. So here you can see a blob here. This is the 50 millivolt thing, which is the main feature, and then the other excitations are weaker and much broader than this one. So although they're weaker, if we integrate them all up, they come to a similar intensity as this. I'll show you. And then we have that's optimal doped. So I should have gone here first. This is underdoped, which is in between these two. So we've got blob again, but less broadness and more intensity here. And then overdoped, then this low energy bit's gone away, and we're left with some stuff which you can't really see because I put it all on the same scale. It's maybe easy to see here where we've taken each energy and integrated things up in Q. And you can see here for the parent compound, we've got this, and then as you go to the superconductor, the intensity is less, but not that much less. And you've got this highly structured thing here. So this peak here is corresponding primarily to the incommensurate scattering. It persists down to the lowest energies for this doping. And here you've got this 50 millivolt blob. And we know now when we dope, actually this feature disappears. At overdoped, and at overdoped actually we get a lot more excitations here down at low energies, which might be connected with this this peak that was shown by Cyril. Okay, so here's some RIXS. So what I just showed you was the neutrons. You see it's kind of limited where we can go up about 150 millivolts with neutrons to measure its evolution. If we switch over to the RIXS, this is some work by Mark Dean and collaborators from Brookhaven. These experiments were performed at the Swiss synchrotron. It's very hard for you to see here, but basically this is the evolution across the phase diagram, and you see the high energy spin fluctuations persist across, so they change much less than the low energy ones that we measure with neutrons. See, these ones are changing quite dramatically. So I guess that's the first message from general message is that the scattering that we measure with neutrons and X-rays are different in that the ones the X-ray ones are changing much less. I don't have a picture from the zone, but let me just come back to. So this is the Brouillon zone. So remember, as we go along this diagonal here, then an antiferromagnet would have the minimum in energy here and here. And the X-rays measure on this side and the neutrons on the other side. So these excitations in the middle here, around pi, change much more rapidly than the ones measured near 0, 0. So here you can see later data then, this is some of our data from this year, where we can see the evolution of the RIXS ones. So this is along two directions. This is through the pi direction. Actually pi is it's going towards pi towards a half. We can't get there with the X-rays, but we can get halfway there, and that would be 0.225 here. So you can see the first bit here. So these are the spin modes in the parent compound, and then when you go to the superconductors, you see this blob that's much broader, but nevertheless there. And as you go to higher doping, it gets even broader, but there's still a lot of intensity left there. This is along another direction. This is along towards pi. This is towards pi 0. So in this data, you can actually see the charge order in this 1/8 dope sample as well. So this is charge scattering. Actually, there's some phonons here as well. And this blob here is the spin fluctuations that still exist at the higher energies. So coming back to the harmonic oscillator that I mentioned earlier on, we can fit all these curves if we just take cuts up here through this stuff. And these are actually just harmonic oscillator fits, plus fitting the phonons that occur at low energies. And you can see actually within the resolution that we have, which is about 40 millivolts, the harmonic oscillator is extremely good fit across actually the whole range of excitation. So these are different dopings. In fact, we even fitted the parent compound with the harmonic oscillator. The damping took care of the resolution function. So this is increasing doping, and you can see the excitation broaden slightly. And these are the two parameters that come from the harmonic oscillator fits. So this is the dispersion of the spin wave, which should be 1. And then for the dope compounds, you can see you get dispersion, and this is the damping here, the red squares. Increasing damping as we go to high doping. Now, an interesting feature here is if we look at going from one zone to the next. So we've got the zone around gamma here, and then the zone around half or pi over here. You see the excitations are not symmetric. The damping is higher, and they have higher energies in this first zone. And as you come to the zone where the magnetism existed previously, they're of lower energies and lower damping. So we don't have this symmetry that you have in the antiferromagnet of the excitations. That's completely allowed because this is a metal. It doesn't have any order. So the overall symmetry of the excitations is the whole Brouillon zone of the metal. The other thing we can do is we've done actually is to compute the wave vector dependent susceptibility from the RIXS. And we've done this by taking our neutron data and matching it up to the RIXS of the parent compound. So we match up the neutron, the sort of matrix elements from the X-ray cross-section. We determine those by comparing our X-rays with the neutrons, which doesn't have any complications. And then we use the same factors to look at the doped compounds. So we can extract the wave vector dependent susceptibility from the RIXS. This is very hard to do with neutrons because we don't have the data up to such high energies with neutrons. But the disadvantage with RIXS, of course, is we can't, because of the energy of the photons we use, we can't get to the pi position. But what you can see is that the wave vector dependent susceptibility is increasing through the zone boundary, the antiferromagnetic zone boundary, towards the pi position here. So most of the response, the strong part of the response is going to be in where the neutrons measure. So this is a kind of summary then of what the spin excitations look like in high temperature superconductors, based on what I've told you. So we've got two probes, one of which can cover the whole range, but is less sensitive to the high energy excitations, and the RIXS, which we can get up to this green line here. Sorry, this green line here. This arrow is actually wrong. It should be here. And it looks something like this. So this is the strong excitations here, the large wave vector dependent susceptibility, and it's weaker here. And as you saw, it broadens out, and then it comes into this zone. And these two excitations around these 2 points are different then. So we'd expect, this shows this 4-peak structure, and this seems to be a broad thing in this zone. So, if we wind back the clock a bit, just to show you how hard it is with neutrons, we did do some measurements at this point a long time ago with neutrons in an optimally doped LUSCO. And we saw this thing at about 250 millivolts here, you can see, but you can see the quality of data is many times worse than the RIXS, but there is still an excitation with neutrons. We've checked our intensity now against this old data, so the two probes are absolutely consistent. It's just very hard work to measure the high energy excitations with neutrons. Let's just switch over to IBCO for a bit. So the pattern is very similar. You have this sort of structured 4 peaks at low energies, and then you get a blob, and then it broadens out at higher energies. One difference with IBCO though is that the low energy excitations are suppressed. There's no stripes or no rotating octahedra in IBCO, so you don't get below the same. These 4 peaks are going down to quite such low energies. And here's some work from Bernhard's group where they've mapped out in more detail these excitations, and they've found that there's this anisotropy that he mentioned between the A and the B direction in the low energy excitations. How much time do I have still?
15 minutes.
15 minutes, okay. So I'd like to just say a little bit about how this might relate to theory in a simple way. So I call this the parent glue. So if one wants to push things and say, well, we found that the spin fluctuations measured near pi change with doping. There are features that are definitely strong near optimum doping, such as this peak at about 50 millivolts, and they disappear as you go further doping. That's exactly what you'd expect if the spin fluctuations were reflecting the pairing energy of the superconductor. One would also expect to be able to see the spin fluctuations coupled to some electronic excitations. Now, in the case of phonons, of course, neutron scattering measured excitations, which were phonons, and you can see here the density of states from lead, determined from neutron scattering phonons, right? And people did tunneling experiments and saw this. You can also see the excitations reflected in tunneling, and they concluded this is probably the main evidence for BCS actually. If you exclude the isotope effect, because many things don't show an isotope effect, this shows that the phonons were the excitations that were strongly coupled into the superconductivity. So you can do a similar thing, or many people have attempted similar things, but this is one I want to mention from the Canadian group, and Tom Timmer's group, and what they've done now here is to measure the optical conductivity, and they're able to correlate their. They can use that to extract the coupling to electronic excitations, and they see the same two peaks that we see in our excitation spectra here. So here, this is optimally doped LUSCO, and we've integrated up in all the excitations in Q and plotted as a function of energy, and you can see these two peaks correspond. So this seems to be evidence that there is these excitations are coupled to the electrons. So in the simplest sort of magnetically mediated pairing theories, one would take the pairing interaction to be the susceptibility here, and we put it into a gap equation, and you can see that this pairing interaction will couple states to give pairing. So if this coupling, depending on this coupling, it can favour a certain sign difference between the two states that it's coupling. So if this, if we have a certain Q where this is large, then you're going to favour states with opposite gap, only for the gap, over the Fermi surface. So we know where our Q is large. It's large. If we integrate now in energy, it's going to be large near pi. And so if one now draws the Fermi surface of the cuprates on here as a circle, then it would be coupling states across here rather than states across here. And so then you can see that a D-wave gap function naturally fits better than an S-wave one here, with the sign change in the gap favoured by the antiferromagnetic fluctuations. If you apply the same picture to the nuclides, of course, you get whole pieces of Fermi surface with opposite sign. Another thing you can do in using what we've observed to say something about pairing is to do simulations in the Hubbard model, and these are some such simulations to see which excitations contribute to pairing and which don't. So if we look on this side here, this is Tom Tinnis and collaborators, Tom Devereux and collaborators from Stanford, on this paper in 2017. So what they've done here is the excitations in red favour superconductivity, so these are the ones near pi, and these ones actually, the blue ones, disfavour it. So you would expect, again, these excitations to favour. So the ones measured with the X-rays then, in this zone actually, it's good that they're not too strong because they would disfavour the superconductivity. And here we have another calculation on IBCO based on Bernard's data, where they've actually worked out which of they're now in the superconducting state, and they've looked at the particular excitations and worked out which ones contribute to the pairing. And you can see the green ones here, which is the mode, the high energy mode above this peak feature, contribute mostly to the pairing. The low energy excitations, even though they're at pi, actually contribute against the pairing.
Can you account for TC?
Can I account for TC? No.
But if you have blue, green PCS, you'll have an estimate whether it's matching is a different question. What number do you get?
This isn't my work, and I was thinking about that question this morning. I don't know what value they get. I couldn't find it in the paper. What an actual value of TC. I guess that's a harder question than just working out whether something's superconducting or not at low temperature. But yeah,
of course, TC is a hard question.
Sorry?
Of course, TC is a hard question, but that's also
I believe it gives you about the right TC, but I don't have a. So finally, just to say a bit about the spin and the charge. In fact, I think some of this has been covered by Bernhard, right? So the big picture, how does it relate? So we've had two talks, one on spin and one on charge. How are they connected? And
also the pair density. I'd like to see all the three come
together. Well, that talk was this morning though, so we can only go back one talk. Okay, so this applies to that as well, I suppose. Superconductivity is intertwined with other instabilities, such as the charge density wave, ... which could be pair density wave. Yes, if we go back to the early to the 80s, then of course, even before the great paper from John Tranquada, Jan Simon and Gunnarsson were predicting charge stripes. So as Bernard said, and I take the same. I've picked up the same things from the same sorts of papers. I guess that the picture seems to be among many theorists is that the driving force behind it all then is antiferromagnetic fluctuations, which I've shown you today are strong, they're of a wide energy range, and exist across the whole phase diagram. And these, not only can these give Yes, so not only can they give superconductive pairing, but the theories from Chubikov and various people suggest that they can also give the charge density wave order, and we've seen that the non-fermi liquid as well may be connected to them. They show strong temperature dependencies and possibly the supergap as well. So they may be at the heart of everything. Okay, and that was just a schematic to show that. So I'd just like to thank some of my collaborators here. So, okay. So these are the my postdocs and students at Bristol, and my collaborators at ISIS, and Diamond, and the SRF where the RIXS work was done. So thank you for your attention.
So would you also be able to detect the pair density wave somehow in neutron scattering or in RIXS?
Well, we've tried to detect pair density wave with neither of those probes with just conventional X-ray scattering to look for the atomic displacements that we've seen with hard X-rays. But yes, I think other groups have tried with RIXS. I've not seen one as far as I know. So there's several attempts. Not seen one in the sense that we only see one peak instead of two. So yeah, but who knows what the relative intensity of the pair density wave and the other charge density wave, or the displacements of the charge density wave are.
So I want to just say one thing about your question. I think to see a pair density wave type of excitation, you have to look in the delta S equal to 2 channel. And so from Bernhardt's talk, when he described RIXS, there was a second term, the sigma 2 term that I was pointing out earlier. In that channel, you would see a delta S equal to 2. Because you want to create a pair and then destroy it. And that would change.
I don't know if that term's allowed with spin half. Maybe Bernhard can comment. He's shaking his head.
Not allowed?
Well, I think they're mostly detecting the charge signal, which is the derivative of every other state, which is and not attempting to detect the state itself.
Yes. Stefan, so about the neutron resonance, I mean, you show one of the possibility that's apparent blue, right? So, but when we measure some kind of collective mode outside, I mean, on the tunneling spectrum, outside the gap, we see some mode, which we believe is related to the neutron resonance. And then the theoretical friends tell us, almost overwhelmingly tell us that that's not the apparent blue. It's the consequence of the sign change. I don't know how to reconcile these two. So that should not be the same thing.
Yeah. So in the interest of time, I didn't speak about neutron resonance. I tried to show you the sort of picture of the excitations, if you like, in a normal state. Yeah. But so the neutron resonance, as I see it, it's a response to the superconducting state. And when one works out the spectral weight in the neutron resonance, say for IBCO, where it's very easy to see, it's only a few percent, maybe 2 or 3% of the total spectral weight, this being a half.
Oh, that spectrum you show is not the BLTC, it's something about this. That you regard as a very good that one.
Yeah, so I would say, this is one of Bernhardt's spectrums. Actually, that's below TC with a neutron resonance. Actually, this one is above T. This is a good thing. So you can see that the neutron resonance actually here in the sense of the change between these two. Yeah. But if you want something to become superconducting, you have to have the excitations there at TC in some sense, right? To start with.
I mean, the peak will start to appear.
It will, but it's a redistribution
I see.
of spectral wave that's
So you're
already-
not talking about this peak below TC.
No. The peak that I showed. So even this one has a peak, and so the neutron resonance, say in LUSCO, is much weaker. So there is a small change, but say this peak here is not the resonance. The resonance in LUSCO will be down here with 18 millivolts. So in IPCO, things have moved about a bit. So you've got a neutron resonance at about 40 millivolts, but above 40 millivolts there's also low spectral weight, which if you believe in the blue, that would be the blue. Well, medium energy.
So if I remember correctly, this morning in Cyril's talk, he kind of commented in passing that there isn't a lot of evidence of interferomagnetic fluctuation. Am I right? Am I misquoting you?
From neutron scattering.
From neutron scattering, yes.
And everything's
So
on
there isn't a lot of evidence of interferomagnetic fluctuation, is what I heard. And I've also heard this statement from other people before. So, and you're presenting to us today that there is actually strong presence of interferomagnetic fluctuation, if I have to condense it. Am I right?
Yes.
So what has changed?
No, can I change? No, in fact, what I say is that the correlation length of this.
Correlation length is short.
Yeah, the
Yeah,
correlation.
yeah.
Yes.
And do you agree?
Yes.
The correlation length being short?
Yes.
Okay.
I agree. But I disagree on whether that's relevant to what Cyril was talking about. Well, that would be disrespectful. So when you add all this stuff up, you add up all these patterns up to over all energies, then you see a broad peak of pi. And that's what those are quotation marks antiferromagnetic fluctuations. Yeah?
Okay.
Just as if you were to take an antiferromagnet and warm up above TC, above its Nel temperature, you see the antiferromagnetic fluctuations. But the difference between that and what you see in high TC is the stuff is much more structured. And in particular, the low energy excitations, the ones that might be related to a Fermi surface or whatever, are structured, they're much sharper. So if you then want to relate those excitations to a thermal property, such as specific heat or whatever, it's these very sharp things. And those have, to say they have a large correlation length isn't, it's not really the point. It's the width of the excitations at low energies is small, and that corresponds to a large length scale. So this peak here, for example, this peak in Q, that's at 10 millivolts. It's quite small, whereas this stuff here is, if I convert this, take this and convert it to a length scale, is much shorter. So the correlation.
What's new? Like, is it like it's been that way all along, and
Yes.
people have been just ignoring it, or?
No, there are some people who don't.
Okay. But are you finding this much more emboldened by RIXS measurements? Or? I'm trying to figure out what is new, like a history lesson.
It's more of a history lesson, yeah. I'm giving you the current sort of picture of our knowledge of the spin fluctuations up to high energies. So I think the basic features, have been there for a long time, yeah. So I'm just putting it together. So now we have, we could put the RIXS and the neutrons together. And I was just trying to make connections, such as this one, where people often say things, I'm just trying to make it. And the other thing I wanted to just emphasize is, how it evolves across, that we know. Sometimes people say, persistence of high energy excitations, right? But this isn't really relevant, because the relevant ones, I would call, quotation marks, medium energy. If we call high energy 300, let's say. Intermediate, yeah. So somewhere like between 50 and 100. Those change a lot.
But is this across all families, like LASCO, IPCO, FISCO?
As far as I don't think there's. People doubt it's any different to the other ones. I don't know, but it's not. It's just there are a lot of gaps in our data, and we probably believe that's the picture, but you know, I'm just giving you what I think that experimentalists think the picture is. Looking at Bernhard, whether he's nodding, yeah.
Right, yeah. So these overall structure of the magnetic excitation spectrum is universal. It's in all CUPRATEs, and then some of the low energy excitations are different in different compounds. Right? Well, you know, and that's also reflecting this, you know, proximity of the stripe state. You know, in this system, you know, it's almost stripe ordered, right? Even at optimal doping. So therefore, you see these very sharp, low energy features that are not present at this doping level in let's say, YBCO. But if you look at, you know, high energies, and even at intermediate energies, you wouldn't be able to tell one way, you know, the IPCO and LASCO looks just the same. It's indistinguishable.
I want to come back to the same point, in fact, and your comment on the width of the peak in what I understand you were referring to be the real part of the susceptibility and the imaginary part. Did I get this right?
That's right, yeah.
So if I take your damped oscillator picture, and all I do is I give my harmonic frequency a Q dependence, as we would like to do to get some description of these magnetic fluctuations, right? So then I have a correlation length, that's the static correlation length of that system. And then also enters the imaginary part. At lowest frequency, it exactly determines this peak there. As I go in frequency up higher, peaks get much, much broader in momentum space because of damping in frequency space. But still, the real part should have a peak, if that damped oscillator picture is right, should have a peak of the sharpness of the low frequency part. And there I don't understand, where is the evidence that the real part has a broad peak in the susceptibility? Because we don't measure it.
Yes. Okay, that's a good point actually. To be fair, I stand on my point that the imaginary bit has this structure.
Has that structure.
Yeah.
That determines the correlation length ultimately. At lowest frequency.
So it is. So you may be right. So you have to do a detailed calculation to see how it sums up in the real part.
Right.
It is possible. I agree with you. Yeah. I'm not sure we really have that information now. Actually.
Exactly.
Yeah. So yes. Yeah.
Okay.
But yes. But the point I guess I'm trying to make is that if you want to understand the excitations and the thermal properties in what's coming from the spin excitations, you need this.
We completely agree on that part. I just
not this very broad thing.
Oh, no, yeah, just wasn't trying to follow because I'm not sure what you're saying. That the important part for the pairing loop is the high energy. What do you call it? High energy? You mean like above the quote unquote resonance, or what is the energy basically?
We're kind of having two intertwined discussions, I think.
Mm-hmm.
So, if you want to understand the interesting data that Cyril showed, which is to do with showing that you have basically acidic heat detects low energy excitations, right? That's these. If you want to understand the pairing glue, then it's the real part that's the relevant thing. So the integral of all energies, and we know that's broad. It may have little peaks in as well, but it's a pretty broad thing, yeah.
Okay.
And that's what I've been trying to show you, that we know how that varies across reciprocal space and across the phase diagram now. Did that answer your question?
Yeah, I think so.
Okay, I think it's time for coffee.